Pre-Calculus Chapter 6 Lesson 2, and we want to look at one more application of the dot product, or a situation where we would use the dot product of vectors. And this is what we call work. And the amount of work done is a product of a force vector times the direction vector, let's say AB. So if you have a force that's pushing an object and moving it from one point to another along a vector AB, the amount of work done is simply the dot product of those two vectors. And work is only accomplished if there's movement. So if you apply a lot of force to something and it doesn't move, by the technical definition here, there is no work accomplished. So we simply need to find the components of the force vector and the components of the direction vector and multiply those together. And we're going to have to go back to something we learned in the first lesson of Chapter 6, and that is finding the unit vector. So let's do an example, and I'll show you how this works. For example, let's say we have a 10-pound force that's acting in a direction of the vector 1, 2, and it moves an object from the point 0, 0 to 3, 0, and we're simply talking about a coordinate plane here. So what we need to do is find the components of the force vector. Now, according to this statement here, we know that the vector is acting in the direction 1, 2. So if I go over 1 and up 2, and I have this vector, then that's the direction that the force is acting in. Now, the length of my vector needs to be 10, because remember, the size of the force, or the magnitude of the force, we represent that by the length of the vector. Now, the problem here is, if I go over 1 and up 2, that gives me the coordinate of these points. This length of this is not 10. And so this does not represent the components of the force vector. This is simply the direction in which the force is acting. So what I need to figure out then is, if I want the magnitude or the length of my arrow to be 10, and I want it to go through this point 1, 2, the question is, what are these components that would make this and this that would give me here and give me a magnitude of 10? So the way to do this, if you remember from our previous lesson in Chapter 6, Lesson 1, if we find the unit vector, that will give us the components where the magnitude is a 1. So we can figure out the components that would give us a length of 1. And then every other arrow along this line is simply a scalar product of that unit vector times however long we want to make it. So if we find the components of the unit vector, we simply need to multiply those components by 10, and we'll have our force components for the force vector. So we want to find the unit vector then of the direction 1, 2. So you remember the unit vector is found by taking the 1 over the magnitude of the vector and then multiplying it times the components. So the magnitude of this 1 and 2 vector, or this vector in the direction 1, 2, would be the square root of 1 plus the 1 squared plus 2 squared, 4, so this would be the square root of 5. So 1 over the square root of 5, multiplying it times, or using it as a scalar in this direction, would give me the components 1 over the square root of 5 times 2 over the square root of 5. Now this is my unit vector. In other words, if I go over 1 over the square root of 5 and up 2 over the square root of 5, I'm going to have a magnitude of 1, and it's going to be in this direction. Now, I don't want a magnitude of 1, my force is 10. So I'm simply going to multiply this unit vector by 10, and in doing so, I'm going to get 10 over the square root of 5, and then 20 over the square root of 5. These then are the components of the force vector. If I go x value, if I go this way, 10 over the square root of 5, and then I go up this way, 20 over the square root of 5, and I draw my vector here, then the length of this is 10, and it does go through the point 1, 2, because that's the direction that I'm going. So finding the components of a force vector in a direction, we find the unit vector, and then we simply multiply that unit vector by the magnitude of the force that we want. Okay, so that gives me the magnitude of the force vector. Now I need to multiply that by the vector that represents how far the object's moved. Well, this is simply a head minus tail. It moves from 0, 0, that would be the tail, to the point 3, 0, that would be the head. So doing the head minus tail rule, I get a direction vector of, whoops, let me get this, 3 minus 0, which is 3, and then 0 minus 0 is 0. So I have my force vector here, and this is my AB vector, so to speak, and so the amount of work that's done is simply a dot product of these two vectors. So let me scroll down here and we'll do a dot product here. So to do the dot product, I take the force vector components, 10 over the square root of 5 and 20 over the square root of 5, multiply it by the other vector, and remember the dot product is the A components multiplied together, so that's going to give me 30 over the square root of 5 plus the B components multiplied together. Well, 20 square root of 5 times 0 is 0, so the amount of work done is 30 divided by the square root of 5, which if we calculate that out comes out to be about 13.42, and these are what we call foot-pounds, all right, and or newtons. Either one would be the units for the amount of work done. So to do a work problem, you need to find the components of the force vector. You'll need to find the unit vector of the direction that the force is acting in, and then simply multiply that by the size of the force. That will give you the force vector, and then you just multiply it by the components of the direction in which the object was moved, and you can do that by simply doing a head minus tail rule, taking into account where the object started and where it ended up. Okay, I'll do one more example of this for you so you can again see how it works. So in this example, we have a 24-pound force going in the direction of 4, 5, and it moves an object from the point 0, 0 to the point 5, 0. How much work is done? So again, work is the force vector times the direction that the object has been moved in vector. Now again, to find the force, I need to find the unit vector of 4, 5, and then multiply it by the size force that I have, or that I am using here. Again, very quickly, the reason is if I go out 4 and up 5, okay, this magnitude is not 24. All right, I need a magnitude of 24 going this direction, so I need to know what would be the component this way and what would be the component this way. That would give me a magnitude of 24. And the way we can do that is we find the unit vector, which gives me a magnitude of 1. Then I can simply multiply that magnitude 1 vector by the size force I need, and that will give me the components of my force vector. So the unit vector is 1 over the magnitude. The magnitude of this would be 4 squared plus 5 squared. Take the square root, so that's going to be 41, the square root of 41. So 1 over the square root of 41 times the vector is 4, 5. So that's going to give me 4 over the square root of 41 and 5 over the square root of 41. That would have a magnitude of 1 going in the direction of the point 4, 5. Now that's a magnitude 1. I want a magnitude of 24, so I simply multiply these by 24. That will give me the components of my force vector. So the components of my force vector would be 24 times 4, that's 80, and 16, so it's 96 over the square root of 41. And then 24 times 5, that would be 120, then over 41. And so these are the components of my force vector. To find the components of my vector, or of my direction that the box or object was moved, I do head minus tail. So this is where it began, so that's my tail. This is where it ends up, that's my head, so 5 minus 0 is 5, and then 0 minus 0 is 0. So I have my force vector, and I have my direction vector. The work done is simply a multiplication or a dot product of these two vectors. So if I multiply these together, the A component, so 96 times 5, that's 450 and 30, so it's 480, over the square root of 41, plus 120 over square root of 41 times 0, which is 0, so the amount of work done is 480 divided by the square root of 41. So making that calculation, that comes out to be 74.96, and again it's foot-pounds because the force units are pounds and the directions are in feet, so multiplying those together, that's where the unit foot-pounds comes from, or again another thing that might be, or unit that you'll see, is newtons. Okay? So force, or work, excuse me, is force vector times direction vector, and again that's an application or a use of the dot product when using vectors.